you know that hundreds of years ago, batteries were the only source of electricity? We didn't know how to generate electricity from the major sources we have today, like hydro energy, thermal energy, etc. However, in 1831, Michael Faraday discovered something in his lab that completely changed the way electricity was generated. He knew that current-carrying conductor generates magnetic field. So, he performed an experiment to check if we can generate electricity using magnetic field. He connected a cylindrical coil made of conducting wire to the galvanometer. Here, galvanometer is a device used to detect the presence of current in the circuit. It deflects only if current is passing through the circuit. Then he started moving a strong magnet bar back and forth towards the coil. When he was moving the magnet, he observed a deflection in the galvanometer. This proved the presence of current in the coil due to moving magnet. However, when he was holding the bar still, the galvanometer didn't deflect. So he concluded that only magnetic field is not sufficient to generate electricity. It should be changing the magnetic field. This phenomena of generation of electric current using changing magnetic field is also known as electromagnetic induction, or EMI in short. The current generated is called induced current. We'll use the same setup to figure out the factors on which electromagnetic induction depends. You will observe that if you move the north pole of the magnet towards the coil, the galvanometer deflects towards the right side. And if you move the north pole away from the coil, the galvanometer deflects towards left. This means now the current is in the opposite direction. Let's try the same activity with south pole. Now the deflection will be left in first case and right in the second case. So the direction of the induced current depends on relative motion of the bar magnet. Or we can say that it depends on how the magnetic field is changing, whether the magnetic field is increasing or decreasing. Now let's try to move the magnet faster. Then you will notice that the deflection in the galvanometer is more. That is because the magnetic field is changing more rapidly. Now keep the magnetic bar fixed and move the coil. You will still observe the deflection in the galvanometer. Now let's perform a variation of this activity where a moving magnet is replaced by current carrying coil, where current in the coil can vary. Take two different coils of copper wire, one with 100 turns of wire connected to battery by means of plug key. Let's call it coil 1, and the other with 50 turns of wire that is connected to a galvanometer. Let's call it coil 2. When we plug the key of coil 1, we can observe the needle of galvanometer jumps to one side instantly and just as quickly returns to zero. This indicates momentary current in coil 2. Once the current in coil 1 is steady, there is no deflection in coil 2. And if we unplug the coil 1, we can see that the needle moves in opposite direction of first. It means the direction of current is opposite in coil 2. From this observation, we can conclude that a potential difference is induced in coil 2 whenever the current through the coil 1 is changing. Let's consider coil 1 as primary coil and coil 2 as secondary coil. As the current in the primary coil changes, the magnetic field associated with it also changes, resulting to change in the magnetic field lines linked with secondary coil, which leads to induced current in the secondary coil. If we repeat the same experiment with more number of turns in the primary and secondary coils, we can see more deflection in galvanometer. And we know more deflection means more current in coil. The current can also be induced in the secondary coil if the current in the primary coil is steady, but we move the secondary coil. And the induced current is found to be highest when the direction of movement of coil is perpendicular to the direction of magnetic field. Let's try moving it parallel to the primary coil. you will not observe any deflection in galvanometer. Just as direction on induced current depends on relative motion between bar magnet and the coil, in this case, it depends on relative motion of these two coils. I know considering all these factors to predict the direction of current might be difficult. However, the good news is that Fleming gave us a simple rule to determine the direction of induced current in secondary coil. It is known as Fleming's right hand rule. Stretch the thumb, forefinger and middle finger of your right hand mutually perpendicular to one another. If the forefinger directing towards magnetic field and thumb show the direction of motion of conductor, then the middle finger will show the direction of induced current. Can you tell me what would be the direction of induced current in this case? If you apply Fleming's right hand rule, you will get. That's all for today. Let's quickly recap what we have learned. We have seen how current is induced due to relative motion of coil and magnet. We saw how change in current in the primary coil changes the magnetic field associated with it, resulting to change in the magnetic field lines linked with secondary coil. This leads to induced current in the secondary coil. We studied EMI, which means the process by which a changing magnetic field in a conductor induces current in another conductor. We found that this induced current is highest when the direction of movement of coil is perpendicular to the direction of magnetic field. Finally, we have learned how to find the direction of induced current by using Fleming's right hand rule. Hope you got to learn some new things. See you back in next session. Until then, keep learning.